edition of the WHO 2022 PitNET taxonomy.
Can you see my screen, Andrea? Yeah, can you see my screen?
Yes, doctor, we can see your screen.
Great. So
we can see your presentation.
So let's kick started. See, no autographs and no introductions. Simply, I want to speak on the topic, and of course, I would like to thank GLOBALSCION Conferences for allowing me to speak up. So this is the topic, and I call it the medical renaissance. It's because beyond 2 let's just forget about the slides. It's going to come one by one. Let's just understand the topic. See, beyond 2022, what scientists, doctors, paths, and surgeons were thinking, they were surgeons, I mean to say the cohort of endocrinology surgeons, they were thinking that, all tumors that happen in the pituitary gland are basically adenomas, simple benign adenomas, with a few, you say, a visual field defect, some bit of hypothyroidism, or maybe some other constitutional features, right? So you see, this is how people used to think before 2022. But there were three things that came to their attention. The first part. And the first part was that no, these tumors, they keep on expanding. They keep on moving to the cavernous sinus. They keep on moving to the sphenoid sinus, then the dura, and then of course the meninges, and they spread. That is the first part. The metastasize. That's the first catch. Then there was frank chemoradiosresistance. And the third pillar, which actually did shook the WHO, was recurrence post-surgery. You go for a surgery of the pituitary gland post-transsphenoidal surgery, or a transsphenoidal approach, and basically after that, even then, when you are removing the tumor, in simple language, you're still having a recurrence. These were the three pillars which made the WHO think, no, there is something wrong with the previous classification. So they did change the entire classification completely. And that's where the entire story of this particular part begins. The reframing. So I told you why this topic matters. There is local invasion, and of course myths after that. There were frequent recurrence and therapeutic resistance. Next one. So what was the previous system? Previous system was something which is very subtle. It was basically on the hormones that the tumor was secreting. Say suppose growth hormone, say suppose gonadotropins, adrenocorticotropic hormones, then PRLs, prolactin. Then the biggest part was the null-cell tumors, which never used to express anything, used to just sit silently, press upon the optic chiasm, and used to cause visual field defects like of course most common visual field defect is bitemporal hemianospia. So these were the few things that they used to do. So I told you there was an evolution, and based on those three pillars, WHO came to the point that no, now we need to integrate or classify the particular tumors based on the cells of origin, based on their embryonic cells of origin in utero. That's the PIT1, TPIT, and SF1. So the focus, that's what I pointed out. The focus shifted from hormone secretion to developmental origin. That's the catch. And that's where we start the discussion, or the story has already begun. The next one. So what's PIT1? Pituitary specific positive transcription factor 1. Then a T-box pituitary transcription factors and stereogonic factor 1. You know what they do? What they basically do? These are transcription factors. Like PIT1, they will differentiate, they will help in the differentiation of somatotrophs, lactotrophs and thyrotrophs. Same goes for T-PIT in the slide. They will help in the differentiation of corticotrophs, and SF1 are going to help in the differentiation of gonadotrophs, and from there you're going to have the tumors that are there in the third column. Some growth hormone tumors, prolactin, thyroid stimulating tumors, plurihormonal tumors, some silent tumors as well. You see this particular term silent, yes. Many of the tumors which are thought to be benign or silent in simple language are not at all silent. They were creating those harakiris and all of that. So I'll discuss all of that. You can see even on the third part, it's null-cell tumor. So for the sake of some lucidity, let us consider that silent and null-cell tumors are all same. The same entity, just for the sake of understanding, for the time being. The next one. So it's, of course, now you see on the new classification that was known as the PitNET. You see, it is on the left hand side you can see it's a benign lesion. On the right hand side is a neuroendocrine tumor classification. Look at the behavior. Last time, before 2022, it was under-recognized, as I told you. Basically, what happens is 15% of the pituitary gland tumors are usually encountered in the regular practice, as I've seen in West Bengal and other states, and of course in India. And you need to have a very robust sense of classification. That is where I have pointed this particular thing out. I have called it a medical renaissance. So you see that behavior. Last time, beyond 2022, before 2022, it was under-recognized, and beyond 2022, it is explicitly recognized. So of course, the prognostic value is going to increase. Before 2022, it was limited, and now it is improved. As simple as that. Let's not talk about molecular integration. Fine, of course, it's going to be, they have encouraged, the WHO, World Health Organization, post 2022, they have encouraged that no, you need to integrate the molecular epigenetics as well. So this is what basically happened. Okay, fine. When I come to this particular slide, let me say that I have gone to 354. I have searched databases like PubMed, Central Scopus, Embass. I have taken up 354 studies, studied them very rigorously, and of course, according to the PRISMA 2020 guidelines, I have selected 10 studies which were of high value. I'm going to discuss one by one, and they're going to prove that okay, fine, this is how the renaissance or the change or the revolution in the medical system or in the medical literature of pituitary gland is totally justified. That's it. The keywords that I had taken, it's PitNET, WHO 2022, took it to right. PIT1, TPIT1 and SF1 and DNA methylation, and talk about this later on. Right. Now, of course, I have taken PRISMA. There were 4 basic outcomes. One, the focus. Where was the focus? The focus was on classification. It was on molecular mol bio. It was on clinical outcomes, and of course, for every doctor, be it of any genre, the prognostic significance becomes a very high priority. The post an intervention, how does my patient behave? And all we need to do, as I've said in my previous conferences, previous GLOBALSCION conferences, that we need to focus on the prognostic significance. How does that improve? The next one. Now, why doesn't this work? It's wrong. So, what was the biological basis of PitNET classification? There were key transcription factors. I have outlined it. Let's not spend much time on this. Of course, I've said an in vitro embryonic lineage was taken into account. So why did it matter? See, in the traditional classification, 20% ambiguity was seen, and now greater than 95% of the lineage assessment is being decrypted, right? So this is a frank decryption of more than 95%, in which, of course, there will be better reproducibility, better biological correlation, and of course, a better prognosis of the patient post-surgery, or maybe even pre-surgery. We'll talk about it. Okay, I have just put out one slide what Yamada found out. 400 tumors were analyzed, and of course, same finding. See, tumor profiling was successful in more than 95, and hormonal classification failed in almost 20%. Approximately, it failed in 20%. It's one of the studies that was an early study, right? So Yamada had done it, Dr. Yamada. So kudos to him. Next one. This is a very dangerous part. Silent corticotroph PitNETs. We call them null tumors. They have nothing. Neither do they secrete hormones, neither do they express any molecular features or any features of mol-bio. Like I have pointed out 3 markers, those are very important. They do nothing, but at the same time they have higher recurrence. They go out and create a nuisance in the body via metastasis, as I have said, that they keep on infiltrating all the sinuses, the dura, and then they move on and they kill the patient. Look at the therapeutic resistance, that is also increased. They are very much resistant to chemo and radiotherapy, right? CD4/6 K inhibitors, mTOR inhibitors, and all that. So this is a very dangerous one, a very dangerous entity. We'll talk about it. So 3 very important examples would be silent corticotroph PitNETs, sparsely granulated somatotroph PitNETs, and PIT1 pluri-hormonal PitNETs. I'll come to this as well. So they, of course, they are very aggressive. Look at the characteristics that have been outlined just above this. 3 tumors: rapid growth, recurrence, sinus invasions, extreme resistance, and of course hormone resistance. That is all it is. Extreme resistance rather. In both the parts and both the paradigms, if you put if you try to shrink the tumor with a neoadjuvant chemotherapy, no, that's not going to work. Number one, with a suppose a drug. If you try to shrink the tumor with some bit of radiotherapy, then that's not going to work. It's very dangerous phenotypes, not genotypes, phenotypes like that. And those are the 3. Right. So what was the revolution? So I've spoken about transcriptomics a lot of times, partial transcriptomics. These are latest models in which we make a three-dimensional structure of the genetic profile of a person with pituitary tumors, and then we study them properly. And what are the exact places where we might have a problem, right? So in this, 2 things that I'm going to discuss. That is DNA methylation and CNVs or copy number variations. Let's start with DNA methylation. So what does this do? Now, in order to understand this is important slide, a very important one. In order to understand this particular part, what is DNA methylation? Now, DNA methylation is something which is very common in any individual. What do? They basically switch on and switch off according to the needs of the body. Like, they will express proteins when they are needed, proteins of any form, right? Number two, of course, they help a lot in cellular differentiation. Rather, how do they help in cellular differentiation? This is one point where we need to understand for a normal person. Like, suppose a cell, a precursor cell rather, that's gonna mature into a skin cell or a nerve cell. So this is the part, DNA methylation, which goes and do ask the cell, no, you mature into a nerve cell, you mature into a skin cell or maybe some cells of the body. Very important. And the third classical part is the XX1 for females. In females, what they usually perform this genetic dosing. Like, for example, what I remember right now at present is a calico cat. So they will only express those loci or the loci of the genes, like suppose an XX1 or a female, only those parts which are important for a proper phenotype. This is DNA methylation. And they do it, how do they do it? DNA methyl transferases, there are a group of enzymes in the body. And they simply go and they stick in a moiety consisting of a carbon atom and 3 hydrogen atoms, 2 CG bases, cytosine and guanine bases, CG bases only, and they start this switching on and switching off process. So now let's just go back and think, if this entire process gets disrupted in any neoplasm, I'm talking about a pituitary one, that's all right, but in any neoplasm, you can easily understand that yes, if this process is hampered, all the 3 parts, the part of protein expression, the part of a gene expression, the part of the cellular differentiation, everything is going to be disrupted. The study was done by Dr. Keeper et al. And when we started studying this particular part, they could predict, of course, like an astrologer, they could predict the quantum of recurrence, the quantum of invasiveness or myths, as you may say. This is DNA methylation that was used to classify. There we go. It's multi-omics classification done by Dr. Neo. Let's not focus much on this part. Transcriptomics, of course, I have said about it. I have said about DNA methylation. And the third one is very important. CNV's copy number variations, will come to that. So of course, the findings will be this. I've said it multiple times, let's not waste time on this part. Okay, no, I need to go back to my previous slide. So CNVs, copy number variations, this is one concept which people would need to understand. See, I don't focus much on slides. I try to make things lucid as per my knowledge, so I'll tell you. What are CNVs? Say CNVs are copy number variations. These are, let's not call it a defect initially. Let's just say that there are some certain genes which regulate a proper differentiation, and they can be identified by microarrays or next generation sequencing, or maybe transcriptomics, spatial transcriptomics. So for pituitary, let's go for SOX3, SOX3, this is one. LHX4 and HX1 are the two other important genes. Let's focus on SOX3 as of now. Now in SOX3, for CNVs, what happens is copy number variations. There, in a normal human being, there must be one copy, right? But for a person with a pituitary neoplasia, there will be multiple copies of this SOX3 gene. One important clinical entity that I remember right now, and I have encountered this multiple times in my clinical practice, is combined pituitary immunodeficiency. It's because of this SOX3 gene copy number variations. That is of paramount importance. So what do? We find that out. We find the culprit. We find it, I said just a few minutes back, I just said that we find the culprit via microarrays or NGS. If you've seen an NGS report, next generation sequencing report, say for example, for a pancreatic tumor, in pancreatic tumors you'll have BRCA1, BRCA2 positive, which is not usual. Right? So we identify those and we try to predict as to where the entire path is going to go. Great. So of course it's going to go for better tumor clustering, better recurrence prediction, better therapy, and all that. That's not important. So now we move on to precision oncology. So what do? Step 1. Of course, we try to find out those particular parts or segments which are responsible, the embryonic cell lineage of a particular tumor. Right? We have a tumor and we try to find those things out using various methodologies. Right? It can be a post-resection or pre-resection. We try to find them out. Number 1, the embryonic cell lineage in utero. Step 2 is molecular profiling. Of course, if you resect a tumor, and once you resect a tumor, we can go for immunohistochemistry, NGS, spatial transcriptomics. When I say immunohistochemistry, there's so many CG markers out there. So that will help in my molecular profiling. And then, third part, once we are done with the entire thing, we go for personalized management for a better prognosis. So for paths, it's mandatory. This tracking of the lineage, the backtrack of the lineage becomes very mandatory. For endocrinologists, of course, it's going to provide a better prognosis. For neurosurgeons, the same, and for oncologists do or the same thing. It's gonna improve the prognosis as we keep on treating the patient. Yes, there are limitations. Of course, the cost is a limitation. I come from India and I know that the cost effectiveness is a big burden. The limited availability of methylation platforms and labs, they vary in their reports. So I would like to focus on the 5th part, unresolved hybrid lineage tumors. You know what? This portion is another one which is very challenging, and studies are on the process for this particular one, in which now these tumors, I said in one of my lectures, the tumors are also smart. Human cells are smart, tumors are smart. So if the tumors are smart, quite smart enough, they can express PIT1, SF1 at the same time. They can express PIT1. They can express all the 3 at the same time. We profile them in that way as well. So this is still, that's what I've written, unresolved hybrid lineage. When I say hybrid lineage, it will carry all the three parts, all the three proteins that I have said about in my first 1 or 2 slides. So, of course, AI is going to help. I've spoken about AI multiple times. Like, I love my forest model. I'll not talk about it much out here. I've spoken about it in my previous conferences. So, it's the AI digital pathology. You can, of course, rely on liquid biopsy and circulating DNA, nothing but some DNAs or some genetic material shredded by the tumor cells, and we just get to detect it. It's quite simple, right? And we can detect them via flow cytometry or something like that sort. So flow cytometry, I believe you know the principle of flow cytometry. We can just put on a fluorescent antibody, and we can check them on the, we can just get to the point with the fluorescent antibody, and we can create a graph and finish it off. So you see, there are targeted therapies. I've said about CDK4/6, about target some rapamycin or mTORs, or there are immunomodulators, right? So we need to personalize PitNETs, and we need to work on that. So what is the take-home message? Of course, it's very much well written. So 2022 changed the literature. Transcription factors immunophenotyping is now central to diagnosis. Those three things that the scientists and the researchers did find out, the brawny scientists, researchers, the extraordinary people. Silent corticotrophs, I've discussed this part. DNA methylation, multi-omics, copy number variations, those are to be identified by flow cytometry, NGS, and spatial transcriptomics. And of course, the future lies in precision immunopathology. It was a pleasure, docs. So, any questions? Any questions from any side? Yes, any questions?
Thank you, Doctor, for your wonderful speech.
Any questions? Where is my browser? Where
Could
is
you
my
please
browser?
unmute and press it?
Yeah, I can unmute. I can also stop my video and I can proceed. Yeah. Any questions, please? I would love to answer. Any questions? David,
Yes.
Andrea, I believe, let me just check on. So many people, right? Professor, Prof. Magnus, Drisha, Dr. Drisha, Dr. Jessica. Dr. Drisha is, I believe, known to me. Can she speak up? She's from the US, I believe. Jean Martin, Dr. Jean Martin, Pathology. Any questions? No questions. Right, you can just, I'll put my mail ID out here in the chat box. Where's the chat box? I am not sure of the chat box. It's, okay, this is the chat box. You can just contact me out here. I can send you, this was published in the Journal of Carcinogenesis long time back. So yeah, I can send you all of that.
Yes. Thank you so much, Doctor, for your wonderful speech. So,
Thank you, Andrea. I believe you
I'd
have
like to
enjoyed
call
it.
Dr. Adebio.
Yeah.
Yes, Doctor.
Yeah. Thank you, Andrea. Thank you. I
Yeah.
believe you have enjoyed it
So,
as
now
well.
I'd like to call. Yes, Doctor. Now I'd like to call Dr. Adebio Ambali, Onojo University, Tumors from Nigeria, to give a valuable speech on prevalence